Hello, current and future RZJHS physics students. I'm Shana Frank.
And I'm Lucy Rowe. We are current seniors and members of the RZ class of 2020.
Today, Lucy and I will be talking about the physics of music and the human voice. Both of us love to sing, so this works really well.
Before we get to music, it is important to differentiate music from noise. Noise is a compilation of random or dissonant frequencies at random intervals. On the other hand, music is organized noise. The frequencies that make music sound nice are harmonious. Harmonies are caused by the ratio of the two notes, the two frequencies. The simpler ratios are consonant, meaning they sound good when played together, while the notes with more complex ratios sound dissonant. All sound is made of longitudinal waves, also known as compressional waves.
The chart on the screen shows all of the different intervals. As you can see, the intervals with ratios that you wouldn't want to deal with in math class are the ones labeled dissonant. An octave, the difference between middle C and high C, is defined as two notes that are 8 whole notes apart. The ratio between the frequency of the notes in an octave is 2:1. This means that the higher note in the octave has a frequency that is exactly twice the frequency of the lower note. The next most natural interval is the ratio 3:2, the perfect fifth, and then the perfect fourth with a ratio of 4:3.
To illustrate the beauty of harmonies, we will sing an excerpt from Always and Forever, a duet I wrote and we performed together at Showcase this year.
Because always and forever I'm yours. No more hiding and closing of doors. Because who cares what the world may say? I won't if you promise that you'll be the one who stays forever and always.
The harmonies that Lucy wrote into this song are thirds, fourths, fifths, and sixths. The third has a ratio of 5:4, the fourth a ratio of 4:3, the fifth is 3:2, and the sixth is 5:3. Because these ratios are not something like 45:32, they're relatively simple, and so they sound pretty together.
There are many ways to make music. Stringed instruments, like guitars, are very common. Strings produce music through standing waves, a wave that has a set frequency but changes in amplitude. Standing waves are formed when multiple waves travel down a path on a fixed or loose end, and it is reflected right back, causing interference, and therefore creates the peaks and valleys that form the wave itself. The points of the wave that don't oscillate are called nodes, while the parts of the wave that do are called antinodes. The system of waves moves in a sine pattern with the same frequency and with a fixed relationship between the phases. This means that they are moving with normal modes of vibration.
The simplest form of a wave is called the fundamental, or first harmonic. This is the most basic wave you can have, with the fewest nodes and antinodes. There are more complex standing waves besides the fundamental, and these are called overtones, which add nodes and antinodes. All fundamentals are related to their overtones, and all overtones are related to each other. Together, the fundamental and the overtones makes up harmonics, with the fundamental being the first harmonic, and the overtones being higher numbered harmonics.
The equation representing the fundamental is as shown. The 1/2 indicates one antinode per half of the wavelength. The second simplest wavelength you can have, the second harmonic, will have 3 nodes and 2 antinodes. The equation for the second harmonic is also on the slide. It has 2 antinodes per half of the wavelength. Following this pattern, the third harmonic will have 3 antinodes and 4 more nodes. For a fundamental with 2 fixed ends, the length of the string times 2 is equal to its wavelength. Therefore, the fundamental frequency is equal to the velocity over the wavelength of the string times 2. To find the frequency of the harmonic, simply take the fundamental and multiply that by the number of the harmonic you want. So if you wanted to find the frequency of the octave harmonic, you would take the fundamental frequency and then multiply it by 2, as the second harmonic is the octave.
The note played by a guitar string depends on the velocity of the wave on the string and the length of the string itself. In order to calculate the frequency of the note, you need to know 2 equations. First, the frequency of the note is equal to the velocity of the wave on the string divided by the length of the string itself. The velocity of the wave is equal to the square root of the tension of the string divided by the string's mass over its length.
The unknown that we will be solving for is the tension on each of the 6 strings of a guitar. In order to do this, we need to measure the length and mass of each string. The length we measured with a ruler, but without taking the strings off of the guitar. We didn't know the mass. However, we called the company that makes the strings and they told us their density. The strings are sold by gauge, meaning by diameter, so we found the circumference and used that and the length to find the volume of the skinny cylinder that is the string.
Once you have the density and the volume, you can solve for the mass. We now know everything we need to find the tension. Once you isolate T, all you need to do is plug in the frequency, mass, and length of each string and solve. The tension of each string is what you are changing when you are tuning a guitar. You cannot control the mass of each string or the length of each string. This means that when you want to change the sound that each string makes, you need to change the tension. The values that we found are the tensions in the strings that make the notes of the guitar on key, and they are the target values when tuning a guitar.
Tension doesn't just affect sounding guitars. The idea of tension can also be related to the human voice. The foundations of classical singing are rooted in having the least amount of tension possible in the body. If one part of the body is tense, then the entire sound is affected. Too much tension causes interesting phenomena such as a flutter, a rapid stream of vibrato that sounds unnatural, an unsteady stream of vibrato, or no vibrato at all. A small amount of tension to none is the ideal, and will result in a louder, clearer sound because there are more parts of the body that can resonate and aren't being held back by the body's or the wavelength's limitations.
This is one of the main differences between pop singers and classical singers. When pop singers normally go for the high notes, they get quieter. That's partly due to tension and simply a lack of training, whereas a dramatic soprano can blast any note above the musical staff all day long because they aren't putting pressure on their body like pop singers on the radio are.
Singing uses the vocal cords to produce sound in similar ways to wind instruments. Wind instruments produce music through air molecules that move in and out of a closed space. The places where they move the most are the antinodes, while the places where they move the least are the nodes. The tube of the instrument acts as an air column, so when sound is pushed through, it causes a pressure wave that makes the container vibrate. The result is a frequency or a note. For the human voice, the entire body acts as an air column for your larynx. The flow of air from the lungs causes a pressure wave which allows the vocal cords to vibrate. The note sung is a product of the tension in the vocal cords.
Terms often associated with singing are head voice and chest voice. These terms relate to the place where the singers feel the notes that they are singing. High notes tend to be felt more in the head, and low notes tend to be felt more in the chest. The higher the note goes, the more the resonant feeling moves upward as well.
The wavelength, when it comes to the human voice, is the human itself, specifically the larynx inside. The longer the larynx, the longer the wavelength, and vice versa. This is why men usually have lower voices than women, as it is scientifically shown that they have a larger larynx. A combination of a longer larynx and more testosterone that strengthens the cartilage of the larynx causes men to have that deep rumble that's normally associated with radio voices. Women, however, have a shorter larynx and less testosterone, allowing their voices to sound higher and brighter as opposed to the voices of men.
When we did this presentation at the 2019 Physics Expo, we invited Victoria Warady and Mark Luban to sing the lowest note that they could into a microphone that graphed the wavelengths that they were singing. Mark could reach significantly lower notes than Victoria. This is because she has a shorter larynx than he does. Her notes have a shorter wavelength and are therefore higher. The graphs show this. When Victoria sang, the high frequency, and therefore the shorter wavelengths, resulted in a higher note. On the other hand, with Mark, the frequency and wavelengths were low, resulting in a lower pitch. The wavelength also comes from the amount of air that a person decides to expend when singing a note. It is balancing this release of air that makes a good singer. Opera singers have that classical vibrato, which is the result of a steady stream of air, or a steady vibration of the vocal cords. A release of air that is too strong will result in a sharp, sudden, unpleasant, or out-of-tune sound, while too little air will result in a sound that no one can hear or is also out of tune. This is what people normally call sharp or flat.
Frequency and wavelength are not the only aspects that affect the way music sounds. Another component is timbre, also known as tone color. Timbre is what makes a C on a piano sound different than a singer singing a C. Timbre allows us to tell the difference between two instruments that are playing the same pitch at the same volume. It changes based on the size and shape of the instrument, the material it is made from, and the playing techniques that are used to make sounds. Vocal timbre is determined based on a person's physical characteristics, such as their lung capacity and the thickness and length of vocal cords. In electronic music, people remove the overtones and just amplify the fundamentals, while in acoustic music and live singing, the timbre reflects the overtones and fundamentals of the sound.
Once you have successfully made the sound, now you want it to be heard in a large, crowded room. The way to do this is with amplification. When it comes to natural amplification, the most common form of it is found in the singer's formant. When opera singers project into a room, they use nothing but their voices and their technique to get the sound out to every person in the space. The bigger the space, the more resonance the singer needs to project their voice, and the more resonance they have, the more likely they are to be able to project to the entire audience. The singer's formant is an example of resonance and a singer using their body to its maximum advantage.
Everything has a resonant frequency, that is a frequency that it is happiest to vibrate at. That is how people break glasses with their voices. All it takes is singing loudly enough for long enough at the cup's resonant frequency and it will vibrate itself apart.
Electronic amplification takes the original sound wave, the one coming from the person talking into the microphone, and converts it into an electrical signal which gets sent down to the amplifier. The amplifier recognizes the electrical signal, which causes the diaphragm of the speaker inside to move, causing constructive interference and increasing the amplitude, the volume, of the original sound wave without the person having to do much. The main difference between electronic amplification and natural amplification is that electrical amplification takes electrical signals and transforms them into sound, manufacturing the constructive interference and increased amplitude that would make something louder, while natural amplification comes from the techniques of the singer who uses their body to produce more resonance on its own without having to use any kind of electrical amplification such as a microphone.
We hope you learned something about the physics behind music, singing, and different instruments.
Let's go sing a lot today.